Hi, this is Howie, and I'm gonna go over the Henderson-Haselbalch equation, and this is used for buffers only. Buffers are solutions that can resist acids and bases, and helps resist the pH change. So anyway, to find that, you can use the Henderson-Haselbalch equation on buffers only, and the equation is as follows: pH equals pKa plus log over its conjugate base and its acid. If you want to look at it any closer, it's pH equals negative log times Ka plus log and A minus and HA concentrations. Alright, so now that you know that, we're going to go with a problem. The problem is that you have two compounds. You have a C6H5NH3 chloride compound, and you also have a C6H5H2 compound, also known as aniline. So you have aniline chloride and aniline. Now we're going to assume that this reaction goes to completion, and when that happens, this will break up into two ions. One a C6H5NH3 plus, and one a Cl minus. And this will actually stay the same. The aniline will remain as is. So we've got our weak acid, part of a salt, and the aniline, which is its conjugate base. So if we're going to do this formula, we're just going to disregard this whole chloride because it's neither an acid or a base, and it's going to be useless to us. And so we've got our acid and conjugate base once again. Now the information that we're given is that this has a 0.5 molarity, and from the textbook, the Kb equals 3.8 times 10 to the negative 10. We've also been told that the pH is already found out at 4.20. So what are we looking for? We're actually looking for the molarity, which is the concentration of this ion, and this is the whole reason why we're going to be doing this problem. Now, to start off with this problem, we're going to use a Henderson-Haselbalch equation, which I just talked about, but to do that, we have to do some changes. First of all, we can't work with Kb because it's from a base. We need to use Ka. So to find Ka, we'll divide the known K water, which is 1 times 10 to the negative 14. That's well known, and we're going to divide that by the Kb that we're given, which is 3.8 times 10 to the negative 10. It actually comes out to be 2.68 times 10 to the negative 5th. So we've got that. Now we can use our Henderson-Haselbalch equation, and that's going to be pH equals pKa plus log over the base and its conjugate acid. Alright, so let's start plugging it in. We've got the pH equals negative log times Ka, which we just found out, which is 2.68 times 10 to the negative 5, plus log over the base molarity, which is 0.5, and that's what we were given, over C6H5NH3 plus acid. And now we're just going to shorten that term to say HA to make it faster on everybody. Anyway, if you recall, we were given the pH already, so the pH is 4.20. We're going to put that in the left side of the equation, and then this negative log times the Ka comes out to 4.58. Alright, so we have that plus log 0.50 divided by HA. Now, how do we get rid of this? We'll shorten it up by putting 4.50 on the other side. That'll give us negative 0.38 equals log over 0.5 over HA still. Now we're going to get rid of log. We're going to use the anti-log, and that's going to be 10 to the negative 0.38 equals 0.5 over HA. Now, to get rid of HA, we're actually not going to get rid of it. We're going to put it on this side. This anti-log comes out to 0.42 equals 0.5 HA. So HA, using algebra, simple from high school, we got 0.5 over 0.42 equals 1.2, and that's going to be the molarity. The answer to HA, which in turn was C6H5NH3 plus 1.2 molarity.